Whereabouts in France? I was in where was I? I was in Paris, obviously, and also Limoges. That's right, Limoges. Limoges. Beautiful city. Anyway, so really what we want to do is, Monaco. Okay, well, good on you, Rene. It's very cold there at the moment, but you've got the big boat show there I see in the news today. Have you been to the boat show, Rene? Hopefully, yes. Oh, okay. And Carol's in London, and I'm in Perth. Oh, okay. I thought it was a big boat show in Monaco. Maybe I'm imagining things. Okay, and I in Perth, end of the year, okay, Perth, Australia. Okay, so we've got people from all over the world. Welcome, and what I want to do in this section is just quickly run through the concept of tuning. Hopefully you can see my whiteboard. Talk briefly about Ziegler Nichols classical rules, then look at some open and closed loop strategies, go into a little bit of advanced stuff which is cascade loops, and then look at dead time. So just to briefly look at that now, and we'll give you an extra paper as well on dead time. So, and as Carol says, be as interactive as possible. So, have any of you guys done any tuning before? What's your background? If you can perhaps just let me know what you do for a, if you've done any tuning in the past, that would be really good. Just text in your box, that'll help me understand the background. Okay, more instrument engineer than control. Yeah, fair enough, yep. I'll just be honest with all you guys. Okay, great. I just want to be very, very honest with you guys. Tuning is a very exciting, very nice thing to do. In Australia, we say it's a sexy profession to be in. I see, okay, thanks, Satish. The only problem with tuning a loop is that you have to depend on outstanding instrumentation. If your instrumentation is rubbish, which is the hardest part of the whole system, tuning is not going to help you much. So let's have a look at the objectives of tuning, and I've tuned many loops, and I'm going to tell you a few little problems I've had at the end of the presentation. First thing is, with tuning, we've got three parameters: PD, set point, and output. So I just want to briefly make sure we're all on the same page here. I'm just going to hop ahead a bit. I'll come back. Yeah, okay, here we are. Here's the right one. Now here's an example of a loop in a very simple thing. Here's the controller, the process controller. This P box there, hopefully you can all see that. Here's the process, your plant, equipment, instruments, everything like that. The controller has an output from it to control the process. The process then has control. Could be, as I say, a valve, a tank, a reactor, whatever. You get an output from the process, which is your process variable. It comes around there, like that. The process variable is then compared to your set point, and the difference is called an error. And that feeds back into the controller. Okay, so are we all happy with the three terms? PD, which is what you measure, set point, our target value, and output, which is the controller output. Are you all happy with that? Please confirm that. Do we understand? We're all on the same page. Process variable could be a temperature, level. Okay, thanks, Rene. So, now, can you all see this diagram, loop, controller, and process? So please give me a little smiley. Okay, yep, control, the output, we call it. Sometimes it's referred to as an MV, which is a manipulated variable. But it's an output from your controller. So in other words, if I'm controlling an output such as a valve, that would be the output going out here. So a valve, for example. Let me just draw a little diagram of a valve. There you are, little valve there. So it's sometimes referred to as manipulated variable. Thanks. Carol appreciates my drawing abilities. no one else does, I would tell you now. Thank you, Carol, for that vote of confidence. So now, can you all see this diagram here? It's very, very important that you look at this diagram because this is the key of tuning. Now, tuning was sort of started in 1943 with two engineers, Ziegler and Nichols. They were the main guys, but it's been around, obviously, since we came out of caves. Now, this process here has a feedback coming back, which is a process variable, and when you're tuning a loop, you've got to make sure at all costs you don't go into unstable region of operation. Can anyone here tell me what unstable region is? Rene, Saha, and Satish, do you have microphones or not? If you don't have a microphone, just text it in the box. Can anyone tell me what instability is? You must avoid instability. Can you tell me what that is, guys? You can take the microphone if you want.
Yeah, can anybody hear me? Just say yes. I don't hear anybody else. So instability, I assume you're referring to a process that goes out its design bandwidth due to bad tuning, instability.
Thanks, Rene. That's brilliant. Yeah, we can hear you very, very well. Thank you very much for jumping in. Basically, as Rene says, what instability is, if I can add a bit to it, is it's got a changing output. So your output from your controller goes like this in a cyclic sortal thing. So that's instability. You've got to avoid at all costs that you go into that sort of region. That is called marginal stability. And you have increasing instability when your output starts going like this, getting bigger and bigger and bigger. So obviously we have to avoid increasing instability because your process can't be controlled then. If you've got a cyclical thing like this happening, you're not going to have very good control. So we've got to choose our tuning parameters so we're always well away from instability. Okay, so this is an example of a loop they're trying to show you here, which is unstable. Now, you need to focus on this. This is really important, this issue I'm going to go into now. The process here will give you instability when there's a 180-degree phase shift in the signal going through the process. Now, what does that mean in simple English? It means that there's a lag or a delay in the process. A lag could be a temperature. Can you think of the time you went to a very cheap hotel? You went to a very cheap hotel, you had a shower, you turned on the shower, but your geyser or the heater for the hot water was very, very far from your room. So when you turned the hot water on, it was cold. You turn up, 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 up. Eventually it gets very hot. It gets too hot. So you then start turning it down again. And then it gets too cold. Then you turn up again and it's too hot. And you have that cyclical control action. Exactly the same thing here. You have to avoid that at all costs. So there was a lag in that example I gave you, and that's why you had to think. So here you've got can you see this here? There's a 180-degree phase shift from there. I'm just going to use a red thing here. There's a 180-degree phase shift here. Goes through the process, and you get a 180-degree phase shift there. Can you see that that's shifted through 180 degrees? Basically, it says that when you're doing your control action, it'll bump there, you get a 180-degree phase shift, and it comes out looking like that. Doesn't matter which way it is, but there's a 180-degree phase shift. So what happens with the 180-degree phase shift is that it feeds through here, it gets subtracted, so it gets inverted again. So now it looks like that. So it's gone from that to that, and it comes into your controller, and it then comes out again looking like that. And what you've got is marginal instability with this process here. So the conditions for instability here are 180-degree phase shift across your process, which, as I say, is equivalent in the real world to a delay between the control action and your process variable. And the other condition for instability, And this is a little bit challenging to squeeze it all into 30 minutes discussion, but it's very important you grasp that. The other condition for instability is the total loop gain, controller gain, feeding into the process gain, must be 1 or less than 1. So if it's 1, if your controller gain is 2 and your process gain is 4, the total loop gain is 2 times 4, which is 8. So that's obviously greater than 1. If the loop gain is, if this process gain controller is half and the process gain here is 2, then the loop gain is 1. The loop gain is the gain for the whole signal going right round like this. So what I'm saying is 2 conditions for instability. If you can't grasp that in a short time, 2 conditions for instability which we've got to avoid when we're tuning a loop. One is ensure that your process gain is, if it's 180 degrees, and your loop gain, which is your controller gain, times by your process gain, is 1 or greater than 1, you have instability. So you've got to avoid, in calculating your tuning constants, you've got to avoid at all costs going anywhere near that situation. Okay, so it's really important. Okay, so as I said, I will pass you all these slides so you can look at them later. So when we're tuning a loop, we said there's 3 parameters we're looking at. Process variable, which is what you're measuring. Set point is your target value, and output is what your controller output is. The first thing is this here is my process variable. As you can see, the process variable changing there. The set point is that change there. So I've made a change to my set point, and the process variable then should follow the set point straight up like that, but it doesn't. It goes like that. So we've got to make sure for best tuning is that this area of error is made as small as possible. Okay, really important that. And similarly, we minimize the amplitude of the error squared. So it's a similar thing to 0.1. The other thing you do is you've got to make sure you minimize wear and tear. In other words, if you're controlling a valve or something like that, you've got to make sure you don't stuff it up. No overshoot at startup. You may have a particular situation where you're tuning and you've got a tank of sulfuric acid or caustic soda, and you say, I don't want any overshoot at all. I don't want to overshoot like that. No, I want something looking like... No, you can always, you don't have to have overshoot. You can have something like that. So my set point's there. And Rene, very good question. Rene says, don't you always have overshoot like that? Certainly, Rene, most loops you look at, you will have a little bit of overshoot like that. But if you have a very slow acting loop, and I will go into the conditions, you may have a loop going up like this, process variable just creeping up slowly. That means it's a very slow responding loop, and it may be for pressurizing a gas cylinder or a level in a tank. You may say, look, a tank has got caustic soda or sulfuric acid in it. I don't want to take any chances. I just want to creep up slowly. So you can actually have that thing. But most of the time, as Rene says, you will tune a loop and you'll have some overshoot because you want a quick response. And the other thing that you know, I always use this word from the Bible or the Quran. Yes, thank you very much, Sir. You're absolutely right. I use this word from the Bible, the Quran, or whatever. Know thy process. If you know your process, you can actually know thy process. Excuse my drunken straw there. You can actually minimize effective known disturbances. Okay, thanks very much. So Rene makes a very good point, our man from Monaco. It makes a very good point there that most of the time you see loops looking like this. And I will look at the conditions for that now, what gives you that there. But the great thing about a loop like that, which is why we use it, with a response like that, is that it's a very quick response. So you don't waste any time. So it's very efficient, you save money, but you may have conditions, safety conditions, where you say, let's creep up the process variable to the next set point. So the most famous guys who created tuning were Ziegler Nichols. The problem with Ziegler Nichols is that they are purely theoretical. Their standard belongs in the university. You don't see it used in a practical world. So I'm going to quickly tell you what Ziegler Nichols is, and then I'm going to say this is what you do in the real world, and there's two approaches followed there. These are two mechanical engineers, actually. Now, the first, there's two types of tuning, and then there's about 10,000 different rules. I'm just going to go through the most common rules. The first one is called the reaction curve approach, and this is very simply, put your controller into manual mode, start running in automatic mode, and you make a step change to the output like that, and you look at the reaction curve, and the reaction curve looks like this. And you then look at the slope of the reaction curve. So the slope could be, for example, the process variable, which could be degrees Celsius for the thing there, and the time will be in minutes. So that could be 10 degrees per minute. So you look at the slope, and you also look at the effective lag. And you see the lag there is that point there, between those 2 points there. So you've got two parameters, two numbers here, and you pop them into an equation like this. And most of the time, as René says, you use PI control, not PID control, PI control. And you pop the numbers in, you get that. So I'm not going to worry too much about this. It's in the slides. So, for example, if your lag is 2 minutes, your T integral you put in will be 3 times 2. Now, there's three types of control here. P control, PI control, and PID control. I just want to briefly explain what they are. The first form of control is proportional control, which means purely, let me just clean this rubbish off here. Geez, so much rubbish here. So we're talking about the controller here. Let me see if I can clean this off. Sorry, I just want to clean this mess off here. Raise drawings. Should have a clean thing here. Okay, there we are. Oh, it's clean. Okay, now what we're looking at is the three forms of setting up your controller: P, PI, and PID. Can anyone tell me what the difference between these three forms of control are? Most of the time we use PI, by the way, but can anyone tell me in 10 seconds what the difference is between P, PI, and PID? Why would we have three different forms of control? Can anyone tell me? We haven't got much time, so I'd really appreciate a quick response. I'm looking at René now. He's probably knowledgeable. Carol, can you say something?
It looks like Satish's coming up with the answer, so typing it in. So type quickly.
Thanks, guys. I know I've got very short time here, so I don't want to waste time, but proportional control, P is proportional control, and what happens with proportional control? If you only have proportional control, you always end up with an error. In other words, when you look at this thing here, for example, if you look at that, let me just clean this screen quickly. Sorry, I've got so much rubbish on this. Okay, if you look at the screen here, if you have proportional control, you'll find that your PD will settle like this, and there'll always be an offset error. So there's what we call an error, an offset error. So what we do is we always add in P plus I control. Yes, that's right. I'll come back to that now, Zahar. So PI control, sorry, my scribbling here is a bit drunken. PI. So you add in integral control, and what integral control does, it gets rid of that error there, and it brings your process variable so it's nice, and it lines up with the set point. So it settles at the set point. So PI controls most of the time. However, if you've got a loop which has got a significant lag in it, let me just find an example of a loop there. If you've got a significant, and I'll come back to a few examples of loops like that. If you've got a loop with a significant lag, just want to find a, here we are. If you've got a loop with a significant lag in the process, for example, a temperature loop, it means there's a significant lag from the time you make a change to the time you get the response. For example, if you heat up a hot water cylinder, the water doesn't suddenly go from 0 to 100 degrees in 1 second. It normally takes a few minutes, hours sometimes. So you've got a significant lag there. If you've got a significant lag in the process, for stability reasons, you will use, let me just get back to that screen, you will use PID control, use derivative control. So derivative actually stabilizes the process. It gives you a quick response, but it tends to help you stabilize the process. Yep, exactly. And eliminates error. Yep, I eliminates error, Zahar says there, but derivative actually helps you stabilize the loop for loops with a lag in them, like a temperature loop. If you've got a flow loop, you will not use D control, you'll only use PI control. And for most of us, common mortals, PI is the name of the game. So that's what we're going to focus on in this little discussion here. So thank you very much for listening in here. Now, the one that's probably the most famous form of control for tuning a loop is continuous cycling by Ziegler Nichols. This is probably the most famous one. These two guys, in mechanical engineers, I hate to tell you, not electrical or automation engineers, mechanical, discovered it. And basically, what they do is they push the loop. When they're looking for tuning constants, they push the loop so that they get instability in the loop. So basically, they push the gain of this controller up until they see instability. At that point, they then work out the tuning constants. The tuning constants are worked out so that they don't go anywhere near instability when it's in normal operation. So the way that you do it here is you increase the gain of your controller, keep increasing it until you see this cyclical action. At that point, it's not increasing or decreasing, you work out your tuning constants, and you work them out from two factors. One is the time, the period of a period is the time it goes up and then back again. Work out the period, and they also work out the gain, and then from that they can calculate their tuning constants. Very simple. So here we are. Continuous cycling. Please remember, this is for universities and academia only. It's not for the real world. I'll tell you how we modify this for the real world, but it's very useful to understand what goes on here. So, and all of you guys here, I've got some software which we can give you. It's a demonstration copy which you use in all our courses. Really good software which you can then experiment later with. It's valid for 30 days, and we use it. It's a very good package. We've got the full site license. So first thing is put your control into P control only. Then you put the values into your controller, what you're using, and you've got three values that you put into a controller: the gain, which is K, T int, which is your integral time constant, and T DER, which is your derivative time constant. So you put I and D to 0. Exactly right. Thank you very much, Rene. Rene, I would like to suggest you do the presentation, yeah, because I think you know more than I do. Can anyone tell me why you put your I and D to 0 for the continuous cycling method? Can anyone make a suggestion there? Why Rene has just said make your I and D 0. Why is that? Any suggestions? Just text it in the box there. Just text it in over here. Just text it in the box. Yeah, that's right. Basically what's happened, and I don't want to go into too much detail here, but basically you can see when we're tuning, we only put the gain or the P control in here. The reason is if you put an integral or D constants into here, you're actually putting a phase shift into your controller, which means you can't work out the true phase shift that's going on in your process. So basically all you're doing is you've got a sanitized, sterile, neutral, whatever you want to call it, controller, which all it does, it increases the gain, and all you're doing is changing the gain value. You're not putting in any integral or derivative control into here, which means that you are looking exactly at what the process is doing with the phase shift. So you're not adding in any phase shift here. If you add a phase shift into your controller, you will be shifting it and thus confusing what you're trying to calculate from the process. So really very important to understand that point. You're trying to identify what the process is doing. You want to understand the gain. Can anyone tell me, in fact, I'm just going to write this down here. I know I'm trying to squeeze a ferocious amount of stuff into 30 minutes or 40 minutes. K loop is the loop, there's the gain of the loop, is equal to K controller times by K process. In other words, if you've got a gain of 4 in your controller and your, sorry, let me just rub that out. Sorry, let me just change that there. If you had 4 for your controller and you multiply it by a process gain of 2, your total gain of the loop is 8. That means every time a signal goes around that loop, it will be multiplied by 8. So, for marginal stability, I said your loop gain must be 1. So in other words, if your controller gain is a quarter, then your process gain must be 4. Okay? Most of the time we work it the other way around. We say, look, the process gain is 4. What must be your controller gain for a marginal stability of 1? Well, it must be a quarter. Okay. So I know I'm trying to squeeze a lot in here, but please bear with me. So the continuous cycling method is put control into automatic mode once you've set it with I and D to 0. Make a step change to set point, and then keep increasing the value of gain until you get that. At that point there, you calculate the period, which is T, could be 3 minutes, and you calculate, and you also get the gain value of your controller. So the gain, the controller, whatever it is, 2 or 3, you put that value in, and then you pop it into, generally, most of the time we have PI control. You're very unlikely ever to have proportional control. Most of the time it's PI control, and if your gain is, say, 4, where you have marginal stability, your controller gain is 0.45 times 4, which is 2, well, slightly less than 2. If your T int that you pop into your controller, if your period is 3 minutes, 3 minutes divided by 1.2 gives you whatever that is, 2.8 or 2.1 or something. I don't know what it is, but anyway, so you pop it in there. If you've got a temperature loop, you'll pop those values in there. Now, as I said, most of the time you're not going to use the Ziegler-Nichols method. You're going to use a modified version, which is slightly different, nothing massive. Don't worry about this because you're running out of time. We use what we call is called the damped cycling method, and all that happens here is we try and get a response curve looking like this. In other words, we don't get a response looking like that because you're not going to be very popular with your plant if you've got a continuous cycling process there. We want to try and avoid instability when we're tuning our loop because we're running a real process plant. So what you do is you have a gradual, you increase the gain value of your controller till you see something looking like this. And from that, we can calculate our tuning constants very simply. It's not much difficult. So damped cycling method is put P controller into proportional control only, so no I and D. Put the controller into automatic mode, increase gain of your controller because you can't change the gain of your process. So you see oscillations. As I said, you always make sure your oscillations look like that. And then you look at the particular waveform that you're using. Stop immediately because you do not want instability in your process, and then you calculate your tuning constants. And the way you do it, as I said, I'll give you all these things. You work it out from a conversion graph looking like this. What you do is you look at your response curve. You can see here delta equals 1, delta equals 0.75. This basically tells you the damping ratio that you have. So if you have something like this, you have a delta of 0.25, because it means it's damping from there to there, it's a quarter, and you pop it in here, 0.25, and you can then work out your PU over P. So generally most of the time you'd be something between here and here, and you can then calculate your tuning constants from that delta factor. And all this is doing is trying to give you an estimated value of what your tuning constants would be, and you pop them into this equation here to work out T int, which comes from here. From this equation PU over P, pop it in there, RD there. As I say, I'm not going to worry too much about the mechanics here. Just want to try and get the basic thing. And you also look at your period as well. So your period is actually the work it out from there. So the idea here is just try and understand the how do we know the process gain? Okay, very good question Satish has asked there. He says, well, what's the deal here, Steve? How do you know the process gain? It's actually very simple. Just to give you an example here, if you are putting if you're putting a control action through there and you see the response here, the process gain is actually the change. It's a very good question. That's just delta PV. Now, it's the change of your temperature or your pressure or your level divided by your change in your output. Can you see that? The output there, the process gain is actually that output divided by that there. It's just like a function box. That's all. It's just a box. So that's how your process gain is calculated. But you don't need to worry about calculating it, because when you're doing your tuning, the calculation will fall out. It'll come out very easily. It's not a big deal. You don't need to worry specifically. But it's very important to understand what process gain is. It's a change in your process variable divided by your change in your output from your controller to the process. It's actually quite an interesting question. In fact, I'll give you a little trick question later. Satish, this is a very interesting question for you, actually. I'll come to you in a tick if I've got a moment here. It's about process gain. Very interesting, and I'll illustrate process gain, because I used to struggle a bit with it. So the other forms of tuning, which Rene mentioned earlier on, which is the thing, tuning for no overshoot and startup, which basically means you go for very, very conservative tuning constants. Can you see these tuning constants here? Extremely conservative. KC here, your gain of your controller, is only multiplied by 0.2, so it's extremely conservative. Very slow move. Okay. No overshoot. And your T-int also very, very small, and your TDR, PU over T, also very conservative. So basically, these tuning constants will give you a very slow moving loop, but you won't overshoot. Another one is if you say, look, I don't really want to have it so conservative, you can actually go for a little bit of overshoot, and you can go for a slightly more aggressive K, 0.33 rather than 0.2, and your T-int here is also a little bit more aggressive. And the reason why T-int, again, I don't want to waste your time here, but basically the formula when you're calculating, when you're looking at integral action, it looks like this, although in the real world it's actually a digital process. I just want to use an analog for example here. Can you see here, this is your integral action, and can you see there, as your T-int gets smaller and smaller and smaller, the more aggressive integral action's happening. I repeat, if your T-integral, so it goes from 3 minutes to 1 minute, your overall integral action gets stronger and stronger. And conversely, if your T-int gets bigger and bigger and bigger, then your integral action gets smaller and smaller. So whereas your TDR, or your derivative control, actually is the other way around, because it's actually TDR times by D, error by DT. Anyway, enough. I just want to briefly mention Cascade Control, because this is a typical Cascade Control situation. As I say, we're a little bit short of time now, and I want to answer Satish's question a little bit at the end as a little trick question for you guys. But just to show you, here's a typical single loop controller. There's your process variable coming in here, because you're measuring the outlet temperature of a tank, and you're doing some control there, the controller, and here's your loop controller here. So you're working out the tuning constants here. This is quite effective, but you will find there's a problem here, because you really need to be monitoring the fuel flow as well. So there's a few limitations with this design. So often you'll have a cascade solution looking like this. Can you see what we've done here? We've put a little fuel controller in here, there, and you've got the fuel measurement, flow measurement there. So it's a combustion chamber here. And basically we've got this loop, the temperature loop, feeding into this flow control loop. First point to make is that this will flow control loop will be PI only, whereas the temperature loop, because there's a significant lag from the time you make an output change there to the time you see this temperature change, this will be PID. So we've got a cascade loop here. So it's very challenging, actually. So basically, you would have a very fast response inside here and a slower response out there. So there's quite a few things you need to know about with PI and PID control here with the Cascade controller. And we refer to the, I always get confused here, this is often referred to as a secondary controller, and this is the primary controller, because this is the guy that does all the grunt work. Okay, now just to give you another little problem that comes along, if you have any process dead time, and I've got a little extract which Carol will send you, if you have any dead time, can anyone tell me what dead time is? The last few little sections of this little presentation are about to start, so another few minutes, guys, and then I'll leave you in peace. Can anyone tell me what process dead time is? Just text it in the box there. Carol? No one's too chatty at the moment. Instrument signal damping, yeah, not far off. Dead time is if you make a control action change. Let me go back to this little loop here. Yeah, as Farai says, Farai. Hello, Farai. As Farai says, Rene's gone. Oh, Rene's still there. Farai says, it's really when you see no change to your output. So, for example, let me just show you here. Trying to find the slide. Oh, there. Okay. Let me just clean this off quickly. Here, if you make an output change here and you see no change in your process variable, for example, you heat up a glass of water or something, or heat up a tank of water and you see no change, that is dead time. So in other words, you've made a step change to your set point or your output and you see no change in the process variable. That is dead time, and eventually it comes up like that, and that time there where you get no response is called dead time. Okay, dead time is public enemy number one for PID loops. I'll repeat that again. I know Carol's probably screaming there with pain. Please don't repeat yourself again, Steve, she's probably saying. But I repeat again, dead time is public enemy number one for PID loops. Okay, really important that. If you've got too much dead time, you may not be able to use PID loops. And if the dead time is significant, you may need to use, oh, thanks, Carol, that's another vote of confidence. Appreciate that. So what I'm saying is with dead time here, if you have too much dead time, you may need to use a thing called a Smith predictor, but that's outside the scope of this discussion. But basically, that's when you may need to look at some sort of other form of control. PID control may not be workable, or you may need a very slow form of PID control. And a Smith predictor uses a PID controller with a model of the process. So, for example, here's a dead time. Here's your feeder with halotype minerals. Feeds it onto the belt here. Here you're controlling the feed in the belt. The thing that weighs the weight of it is some way down the belt. So can you see what happens here? You dump stuff onto the belt, so your output is at 20%. You measure, and you see 0. So then you ramp it up more. So you keep ramping up your output, and you're still seeing 0 coming out there. And eventually, this stuff arrives, and of course you've got this massive load of stuff coming along the belt, and at which point you start ramping it down again. So the problem with dead time is that it may make your process unstable, and that's a big hassle. Okay, so just last things, that's something that you need to watch out for in the future. But just to quickly summarize, level control, PI control is very good, very easy, medium response, tune as slowly as possible without overfilling. Flow control, very easy, also PI control. You'll never use D control. You'll never have instability with flow control. And then finally, temperature control. This diagram doesn't come out too well, but basically it's a major process lag and dead time. You will probably use PID, and you must make sure no oscillations, which is instability. Okay, so just one last point, just before I go. You may find, to come back to that question earlier on about process gain, if I sketch this out here, let me just sketch it out there like that. If you've got a tank looking like that and you've got a flow, a level measurement, just to show you what gain means, process gain means, can you visualize what's happening here? If I've got a tank and I'm filling this up with water, so we've got a little valve here, and I'm controlling this valve, change the color to green, so I'm controlling this valve, and I'm also got a little controller here, so that's the output. And this is the PD. Excuse my drunken scribble, and then set point. Can you see here that if you're controlling over here, you put a little bit of liquid in here, what sort of change in output will you see? You will see a little bit of change. If you are operating down here, can you see that when you put in a cubic meter, a liter of water, the level will change a lot more. So the gain over here, the process gain, is considerably more than the process gain here. Can you see that? Tricky to understand, but remember what I said about process gain? Delta PD, the change in the process variable, divided by change in output. So a little bit of liquid coming in here will make only a small change here, so your process gain is small there, it's smaller there, and this is considerably bigger here. Okay. Which means that when you're tuning a loop for these two scenarios, you will have different tuning constants, and this is why there's often a problem. Anyway, I must leave you guys in peace. I just want to thank you very much for listening in. If there are any questions, please shout. I just want to thank you, Carol, very much for hosting this meeting from London. And Farai, Renee, Saha, and Satish, thank you very much for joining us here. We will make the presentations more interesting in the future, and you'll find it easier to tap in when you need to log in. So over to you, Carol. Thank you very, very much for you guys for all attending. I really appreciate your interaction and your nice questions. Really appreciate it. Very kind of you. I'll just pass it over to Carol, and she can close the session. Thanks very much, guys. Stay in touch, and we will send you the recording plus a set of notes for this as well. Thank you very much. Bye.
Thanks very much for that, Steve. I think everyone will agree it was a really interesting session, and you covered an awful lot of ground in quite a short space of time. As Steve said, we've recorded the session, so we'll be sending it out to you in the next couple of days with the slides and the software that Steve mentioned. Keep an eye on the EIT website for details about the future webinars. We do these live sessions approximately once a month. It's usually the last Wednesday of each month. So keep an eye on it, and hopefully we'll see you in some future sessions. Thank you very much for joining us.